Hello everyone, I am Rajneesh Kumar Jha from Integrated Masters of Physics batch from IIT Roorkee, and today I will be demonstrating the experimental conduction of study of Hall effect, and this is a part of the coursework of course PHN 310 Applied Instrumentation. So let's get started with the experiment. Our aim of the experiment is to study Hall effect in two semiconductor samples. One of them is P-type and another one is of N-type. So the task is to first study the Hall effect by plotting the variation of Hall voltage versus the applied magnetic field, and then determine the Hall coefficient, and using the Hall coefficient then we can determine the charge density and mobility of the carriers. So the apparatus required for this experiment are, on the top we have a digital Gauss meter for measuring the magnetic field, which is created by this apparatus, which is specifically used for creating magnetic fields using these two Helmholtz coil. And the next we have a Hall effect setup, for which we have two terminals which supply current to the probe, to the sample, and the another two terminals are for measuring the voltage across the sample, the Hall voltage. For this we are taking the first sample. For the first samples we have 4 contacts, one for applying the voltage or current, which is along the horizontal direction we apply the current, and along the vertical direction we measure the magnetic field. And we have connected the terminals accordingly, red and black corresponding to positive and negative terminals, to those corresponding on the setup terminals. And after connecting those, we have another current supply for powering the coils of the magnetic field. And this is the another sample which we will use later. And the other things that we have are the Hall effect probe, which basically measures the magnetic field, and corresponding to magnetic field it returns the value there. Right now we have set it to 0. So that's what our experiment setup is. Next we come to theory. For theory, we consider a slab of conductor of length L, width W, and thickness T, and the coordinate axes are specified as this, x, y, and z, and the magnetic field is applied in the positive z direction. The current flows along the positive y direction, and as the current flows along positive y direction, electrons flow opposite to that is along the negative x direction, and due to Lorentz force, the electrons are attracted towards the negative x direction, and as a result of which there is development of negative charge here and positive charge there, and due to which there is a development of another electric field which goes along negative x direction. And this electric field counters the drift caused by the magnetic field for the electrons. At the equilibrium position, the Lorentz force is exactly balanced by the electric field, which we call the Hall electric field here. And solving for this, we get the relation between Hall voltage and applied magnetic field and the applied current. So after doing all this analysis, we get Hall voltage proportional to the current and the applied magnetic field, and linear in both of them. And the other proportionality factors include a constant which we called as the Hall coefficient, and another one is the thickness of this material. So we can see that by plotting variation of Hall voltage with both current or magnetic field, we can obtain the value of Hall coefficient. And using this Hall coefficient, we can do further analysis to determine the charge carrier density and mobility. So coming to Hall coefficient for electrons is given by negative of inverse of this 1 by minus 1 over Ne, and in general we can generalize it for any type of charge carrier, and in that case the Hall coefficient will be given by 1 by Nq, where we have incorporated sign of the charge in the variable Q. So using this relation, we will study the Hall effect here. We will plot the variation of Hall voltage with magnetic field here first, and then current at constant current and magnetic field respectively. And the slope in that case will be given by R over T, times I when we are varying Hall voltage with respect to the magnetic field. So, by studying these parameters and determining the values of VH for corresponding magnetic field applied, we can calculate the slope, and using that slope, we can calculate the value of Hall coefficient by this relation. The slope is given by Hall coefficient times current divided by the thickness. So, Hall coefficient we can determine as slope times thickness by the current. The next thing we will do is the conduction of the experiment. For conducting the experiment, we have attached the magnetic sensor to this clamp stand, and now we will attach the sample to it. But before attaching the sample, it's important that first we start with configuring the sample. As you can see, we have 4 probe terminals attached to the sample, and we need to adjust those probes so that when we apply a current to it, in absence of magnetic field, the current should be 0. And as you can see right now, for applying a sufficiently large current, the Hall voltage detector is negligible. If we even change it slightly, the Hall voltage will vary, the measure voltage will vary greatly. So, in order to obtain precise results, need to ensure that the contacts are maintained such that in presence of 0 magnetic field, the Hall voltage developed should be 0. So that you can adjust by adjusting the sliders. So right now, we adjust a little. So right now it comes close to 0. That's sufficiently close to 0, and even if some stray error remains, we can subtract it from the measurements. So after adjusting the probe and the sample, we now adjust it along with the clamp stand. After adjusting the clamp stand, we put the setup inside the magnetic field. And we need some adjustment, we lower the stand. One thing we need to consider is that the magnetic field measurement probe should be almost in middle so that we get precise values. Okay, now let's see the digital Gauss meter. As you can see, we are having some stray readings. So to eliminate that, we can subtract those values from the measurement values we take. Okay, so now we adjust the current. We have adjusted the current value to now let it become stable. The current is 2.59 milliamperes. That's our value for current. We will keep it fixed, and now we will vary the magnetic field by varying the current supplied to the coils and take the measurement corresponding to Hall voltage from here and the magnetic field from here. And since you can see that we have some stray magnetic field, we need to subtract that from all the readings. And at this value, the Hall voltage is 0.1 millivolts. And this is also a stray value, so we need to subtract it from all the readings. So we go next corresponding to Hall voltage of 0.2 volts. That is, we need to take the measurement at the point where the value just changes to 0.2 millivolts. Okay, so at this point we have Hall voltage 0.2 volts and magnetic field as 156 Gauss. It's pretty close to 2, that's why it's fluctuating. The next value we go to is 0.3 millivolts. 4.3 millivolts. The magnetic field is around 200 Gauss. Similarly, we go next and increase further. For 0.4 millivolts, we have magnetic field around 244 Gauss. And now let's take 2 to 3 readings more. We adjust it to 0.5 volts. And at that point, we have around 287 Gauss. Next, we go to 0.6. Okay. 3 again. 4.7, we go like this. For 0.7, this comes out to be 383 Gauss. And one more reading. Okay, so we can continue this fashion and take more readings. So for this experiment, we have taken Hall voltage when the magnetic field is increasing. Similarly, we need to take another set of readings when the magnetic field is decreasing from a set value to almost zero or the least value, and corresponding Hall voltage measurements. And from these two graphs, we need to calculate the slope. And from the slope, as I mentioned before, from the theory, using the slope, for this case, we have VH proportional to B, and we know VH is Ri divided by thickness times B. So this is our slope. From this, we get the value of Hall coefficient as T by I. I we know, and thickness we have been already given, and it's about 0.05 centimeters. And I we already have taken 2.59 milliamperes. Using these two values and slope which we get from this data, we can calculate the value of Hall coefficient. And using this Hall coefficient, we know R is 1 by NQ. And also, first, depending upon the sign of RH, we can determine the type of the material as well. And as we can see here, that for for given value of magnetic field, as it is increasing, the value of Hall voltage is positive. So from this we can conclude that since this is positive, the type of charge carriers have a positive sign. So Hall coefficient is positive here, which implies a p-type material. The sample which we have provided was a germanium semiconductor. So we can conclude that the germanium sample provided here was doped with p-type material. So that's the first part. The second part is plotting a variation of VH versus the current, which we can also do here. So for this, we keep magnetic field at a specific value and plot the variation of I in milliamperes versus, which is the current applied, and versus the magnetic field, versus the Hall voltage that we obtain. We do it in a similar manner. We first fix the value of magnetic field at some point, say some high value around 600. So we'll take this value around 659 Gauss. and we first let the current be 0 and take the corresponding Hall voltage measurement also, and then we slightly increase the current to a here the Hall voltage has just changed to 0.2 and the corresponding current is 0.37. Similarly, we take further measurements. And we can continue in this fashion. And as we have mentioned before, that since Hall voltage is linear in both current and magnetic field, we can determine Hall coefficient from this data as well. So these two parts constitute the main part of the experiment. That using this experiment, we have studied the variation of magnetic field and the Hall voltage, and also the variation of Hall voltage with the applied current. And using these two data sets, we can calculate the value of Hall coefficient, and using this Hall coefficient, we can determine the value of the charge carrier density, and also we can determine the value of the mobility of the carriers, where the mobility of the carriers is given by RH times sigma, where sigma is the conductivity of the material, which we already know here and are provided with. So that constitutes our experiment here, and as a part of this video, I would like to suggest an application of Hall effect based sensors. So using Hall effect sensors, I have designed an equipment which can be used to measure speed. So here is the basic diagram, how it works. So we have a shaft which is rotating with a speed omega, and with the shaft we have attached a metal tooth wheel, and this metal tooth wheel is in close contact, is nearby to a solenoid which produces an almost linear magnetic field, and beyond the besides and after this we have a sample in which we will study the Hall effect. What happens is that due to magnetic field, there is Hall voltage set up across these terminals A and B, and we apply current across terminals C and D. By measuring the Hall voltage across A and B, not just the Hall voltage but its variation due to the rotation of the tooth wheel, since what happens is that as the tooth wheel rotates, the wheels come in front of this solenoid, and this causes the magnetic fields to concentrate within the wheel a little, and as a result, at the end, at the receiving end, where the Hall effect probe is there, the magnetic field changes, and this change can be measured by the voltmeter, and by sensing the change in the Hall voltage with time and amplifying the signal, we can count the number of peaks. Let's say the Hall voltage varies like this. So by setting a cutoff voltage and measuring the number of peaks after amplifying the signal, which feeds the data to the counter, using the counter we can count these peaks, and coupling the data with the timer, we can obtain the speed output. So that's how basically we can use a Hall effect sensor to measure the speed. And that concludes our discussion for Hall effect sensor experiment and an innovative idea using this Hall effect to measure speed. And thank you.